Okay, so this is a quick video on, in general, finding trying to get at the instantaneous velocity by numerically using the average rate of change to get the instantaneous rate of change. And this is, for those of you in my class, this is similar to homework 1, number 19. So if you're having trouble with that, this will help you. So the idea is you're given this position function, s of t equals t squared plus 1, and you're asked to use some average velocities to try to figure out what the instantaneous velocity is at 3. So we're trying to find the velocity at 3. That's the question. And we know that average rate of change is not the same thing to instantaneous rate of change. Because average rate of change is looking at all the velocities over an interval and averaging them. And instantaneous rate of change is, or instantaneous velocity is how fast the object is moving at that exact moment in time. And that's what we're looking for, is how fast is this object moving 3 seconds into the time that's been recorded. Okay? So I call this the nearsighted numerical approach, because what you're doing is looking really close at the graph, but since we don't have a graph, we're looking numerically very close to the graph. So we're calculating average velocity over intervals, and we're making those intervals smaller and smaller and closer to the actual place I'm looking for. So you can see here, I've done some work ahead of time just to speed up the video. So I calculated the average velocity on the interval from 3.1 to 3, the average velocity on the interval from 3.01 to 3, and so you can see that this first interval is pretty close to 3, but notice this next one's even closer to 3 and it's smaller, and this third one is even closer to 3 and it's even smaller. And then on the other side, this is the same size as that one up there, but it's on the other side of 3. It's less than 3. And notice I get closer and closer this way. Now, how am I calculating average rate of change? Well, basically, I'm going S of, in this case, 3.1 minus S of 3 over 3.1 minus 3. And this should look very familiar to us even before this class, because that's really just slope. You're taking a y value minus a y value and dividing by an x value minus an x value. So the change in y over the change in x is how we calculate slope in general. But it's also how we calculate the average slope over an interval, which is the average rate of change, and in this case it ends up being velocity. Why is it velocity? Because this is a position function, so if I'm taking a position minus position, that gives me a distance. And if I'm taking on the bottom a time minus a time, because that's what we're inputting is time, so this is going to be change in distance on top, change in distance on top, and change in time on the bottom, and that is velocity, change in distance divided by change in time. So I did the calculations arithmetic ahead of time so that we could flow through this. So notice when I calculated average rate of change on this interval, I ended up with 6.1. When I calculated average change on this one, I ended up 6. Now these, of course, I'm not including the entire number, I'm just rounding off. I used the table in my calculator, so it didn't go very far. You might take these numbers out a little bit further, and so you'll get a more precise answer out here. You still won't be exact because it is a never-ending non-repeating decimal, I think it ends up being. Well, actually, no, I think these are, because of the nature of the function, I didn't abbreviate that. That actually is just the answer. So anyway, but the point is that I'm getting so close here that it's actually getting close to the actual instantaneous rate. But notice you can see this happening. This is 6.1, that's 6, and that's 6 again. But when I come from the other side, it's 5.9, 5.99, and 6. So as I come in from both sides of 3, the average rate of change is getting closer and closer to 6. And so what we assume is the average rate of change of 3 is 6. So really what we're doing numerically is we're taking the limit of S of t sub 2 minus S sub t sub 1 over t sub 2 minus t sub 1, as t sub 2 approaches t sub 1. That's really what we're doing, isn't it? But we're doing it numerically instead of algebraically. So you guys have been working on evaluating limits algebraically, and we've talked a little bit about what that looks like numerically. So here's a more kind of fleshed out picture of what that looks like numerically, that we're actually plugging in numbers and we're getting closer and closer to the x value. The one t value is getting closer and closer to the other t value. And so this is the idea of a limit. We're going, and the reason why I call it near sighted, again, because we're kind of looking here, and then we're looking a little bit closer, then we're looking a little bit closer, and looking a little bit closer. And as we see that, as we look at those closer and closer values, we can see hopefully what it's approaching. And you can, of course, do the same thing on a graph. You know, a graph that goes like this, and I don't know what happens there. I can go in and look. You know, I can look. Here's my eyes looking. I can look right there and right there, and then I can look right there and right there, and then I can look right there and right there, and I can see the graph is approaching that point right there, even though it doesn't get there because there's a hole in the graph. I can see that the graph is approaching that point, and that's what we do when we're talking about limit. So the limit is asking, what point am I approaching? So that's a quick video on finding, approximating or estimating average rate of change numerically using, approximating instantaneous rate of change numerically using the average rate of change.